Hello, today I'm here to present my project in the translation of written text between two languages. Let's get started. So let me start with what is actually machine translation. Essentially, machine translation is just translating text from one language to another. So for instance, English to Spanish, Spanish to Japanese, Korean to Norwegian, just any type of translation just generated from a machine. And it's especially important nowadays for travel, business, learning Spanish, for instance, and cheating, like whatever. But it's definitely used in a lot of industries and a lot for personal use. And the biggest name that most people definitely have used or would continually use is definitely Google Translate. Okay. And so just to give a really brief overview of what just the history of machine translation, originally it was more of a rule-based machine translation. So for instance, if you were to translate something like a girl eats an apple or something, and you want to translate it to another language, let's say maybe German, you'd have to actually build rules based around each individual word and how it'll map, to German, for instance. For instance, you break it apart and you break it apart. So for a girl eats an apple, and you map them to German, then you map the actual rules and all the grammar between them. And then eventually it switched to example-based machine translation, where essentially it's looking for bigger chunks. It's still kind of like a sentence pair system, but it's not as single word corpora based. So for instance, with a bilingual, you'd have a target English corpus, and then you have a parallel Japanese one or whatever. And essentially you translate little chunks of it. So for instance, you say something like, how much is that red umbrella? Then in Japanese, you focus specifically on a chunk of the red umbrella, you translate that chunk. Later on, it switched to more statistical machine translation. Essentially, you're finding huge corpuses of either words or phrases, and you try to map them regardless of the length, and just hope they work, basically. And it worked pretty well for a while. But nowadays, especially since like 2016, we use more machine learning, so more deeper networks. So we're using neural machine translations. They're definitely powered by RNNs, specifically LSTMs. Essentially, what they do is they go break down a sentence piece by piece and go along it just to see how it maps well to one another. It codes that into a vector, and it passes that through into a decoding vector where it hopefully translates to what language you're interested in. So that being said, machine translation is not perfect. There are many things it is bad at. If you've never looked at any Asian languages, you know there's a lot of missing chunks. So it is especially bad with rare words and words that's never seen before. Essentially, it has been trained against it, so it has no clue what it is. So there are many things, many newer ideas to get around that. And this picture is just to give you an idea of Google basically released a research paper documenting a zero-shot translation, which essentially, this is showing a projection of it, showing just how certain word pairs cluster together. And essentially, that red area right there all represents one specific word, which in English specifically is the stratosphere extends from about 10 kilometers to about 50 kilometers in altitude. And so if you look at the other sentences here, it specifically Korean and Japanese with the exact same meaning. So the idea behind zero shot is basically you haven't specifically taught the model these sentences, but you hope that there's associations between it, so it jumps between models. For instance, if you had a Korean to English, then you had an English to Japanese model, it's hopefully you can maybe jump from Korean straight to Japanese. So that is the hope. So what I wanted to do is I wanted to see if I could build a simple machine translation model that could learn about explicitly being trained to words as well as potentially deal rare words. So essentially, to build a translation model using multiple ideas proposed in research papers, including the zero-shot translation, and this model is definitely going to be built on the seek-to-seek based models using deep neural network, basically. So before we get into what I did, let me give you an idea of what the gold standard is, which has been published about 3 years ago, about what Google did. Essentially, what they have are very deep networks of an encoding layer, followed of attention layer, and a decoding layer, which leads to just the probability vector. So for instance, if you wanted to translate Spanish to English, your Spanish would go through the encoding layer, and they have 8 layers of LSTMs, which get fed into the attention layer. The attention layer will be fed back eventually, but the decoding layer will ideally translate what you wanted from this Spanish layer into the English layer, and ideally predict a good translation up in the softmax. In addition to that, in the first layer, they actually use a bidirectional LSTM. Essentially, the goal of this layer is to actually deal with different languages, essentially. So for instance, Latin-based languages go left to right, but if you go to Asian languages, you might read it right to left. So this is ideally what they use to actually take care of that. So the data set that I've actually used is publicly available. It's on manythings.org.enki. There's a bunch of other languages if you want to play around with it. But essentially what I used is Spanish to English and French to English. And what I specifically did was actually break it down. So I translate from Spanish into English and then English into French. And ideally, if I were able to do zero shot, it'd be able to do Spanish to French. Okay, so about the actual hardware itself. I did this just like Google Colab. So they offer a free GPU, a Tesla K80, which is really strong, 12 gigs of RAM, which is plenty if you're using a embedding layer. If you were to do a one-hot encoding, you definitely will run out of memory. So don't do that. Software-wise itself, it's pretty standard. NumPy. I used that just to trim off some of the padding layer. Matplotlib and Seaborn are just common plotting libraries. Pandas for the data frame support. For Keras, I did end up using a developmental version. It's only because when I was using the metrics to assess the accuracy, for sparse categorical accuracy, essentially there's a bug with the older version released with 2.2.4, which doesn't reshape the data you need to be able to actually use the accuracy metric. So the developmental version actually fixed that bug. RE for regular expressions for a little bit of cleaning, NLTK just to do some blue score testing, and scikit-learn basically just to split data sets between training and testing. Okay, so one of the major keys that was used in the Google translation model is essentially they broke, rather than using your typical word to vect, where you basically turn a word into just a vector, or you do a character-based model. They use the word piece model. And essentially, what a word piece model does is actually, it just breaks it up into subwords. So rather than the full words, it's just chunks of it, so you know basically where the spaces are, as well as what are the most common and important words. So, for instance, for this example, we have jet makers feud over seat width with big orders at stake. But then it breaks it up, so you have this underscore, which basically tells it it's a space, or beginning of jet, and then you get the underscore again, of makers, feud over seat width with big orders at stake. Essentially, there's a model basically that you can just specify how many chunks you want, and it'll make it basically. So to go over, I made multiple models, but this model is, I would say, the more complex model I made. Training time takes about 20-25 minutes at a POC, using about 80,000 sentences and encoding or the word piece model of about 750 different chunks. Essentially, there's an embedding layer because I don't have it. Well, essentially, there's not enough memory to actually use one-hot encoding for 750 for so many samples. So embedding layer made sense. There's a bidirectional to try to emulate, just in case it's a right or left, hand, character encoding. Then one 4-layer stacked LSTM just for the encoding layer. Just ideally, it more fine-tuned it along the way to just define what defines whatever target language it is. And then this repeat vector, just because I just wanted the end result for the LSTM for the encoder. And then for the decoder, I used another stacked LSTM, which basically goes from small to big. Ideally, they learned just how to break up and translate just like text back into the target, basically. And then the softmax to actually take care of actually the translation of that. In addition, I use dropout and recurrent dropout to try to deal with the overfitting that will likely happen because of this. I have a second model. It's much more simpler in that I still use an embedding layer and I still use a bidirectional LSTM, but I do not go through all those dense stacked layers essentially. Ditto for the decoding layer. So essentially there is no stack layers. It's much simpler. Just one bidirectional and a repeat vector and do the decoder. I don't know if I mentioned it earlier, but the optimizer I use is Atom at a 0.0001. My loss metric being sparse categorical cross entropy, and my metric being sparse categorical accuracy. If you don't want to actually use this metric to measure accuracy for your history, your accuracy plots, you don't need it, but then you also won't need to actually use the developmental version of Keras. So either way, it's up to you. Okay. Then for the accuracy, this should actually say model 2, but essentially the model 1 took way too long to train and it was not very accurate. So when I actually ran through some sample phrases, it was basically giving me mostly garbage. Like, not even correct language, it's just garbage. But the number of POCs that I ran for model number 1, ended up being 10. So model number 2, which is this one with the much simpler design, went through 30 epochs. And so you can see the accuracy went up, while the loss is still going down. Doesn't look there's any major issues with the epochs right now. Okay. This might be hard to see, but I made a translation class to make it easy to basically input your string that you need, and automatically take care and input the the string that you want and what your target language is, so French, Spanish, English. Then a function inside of it, which essentially it takes care of all the fixing the data, pre-processing the data, so appending the token that you need, quick error just to tell you if you failed, then mapping it back to the word piece model, and then padding it to the maximum length, doing the prediction, trimming all the padding actually right here from the end, then decoding it using this function up here, which essentially decodes it from the word piece model and returns that back. And so these are just a summary of results I got. It's not perfect, obviously, but it's at least most of the concept is there. So, for instance, in my model, I trained the data of English to French in one combined data set, combining of Spanish and English from the French vector. So essentially, it should be Spanish to French for zero shot. So in that mixed corpus, I had English to French, and so I am here. This looks kind of like gibberish, but J is at least I in French. This looks like it's probably gibberish, but it does seem to know it's French. Then this one, where Spanish to English, donde está el baño, which means where's the bathroom. This is not right at all, but it at least knows, that it's in English. And then with the zero shot, Spanish to French, donde está el baño again, and where's the bathroom? This is all little bits of French pieces. So like not is not, but it does seem to know. It does seem to translate from Spanish to French to some degree. It's not perfect. In addition, just to test whether or not it break, if I give it complete garbage, I put down a sentence, I dic el gato es marvelux, which essentially is all three languages. You get garbage, but it doesn't crash. It's great. Again, just another example showing you also knows baño in English without the question marks, without any of that. It's where is the, so at least it knows where is the. In this case, so the punctuation might actually be very helpful in this case. They're doing it for French. Donde está el baño in French. So this is apparently going through the English side, but it's not exactly French, but it is doing something. And so, the simple model is capable of some level of translation. As we can see, it can tell you some parts of it. It's not perfect. There's no attention layer, so it's not great. And it definitely wasn't trained nearly enough. But as well as some levels of zero-shot learning can be seen. It's not great at all, but it definitely knows it's French. So that is one thing, because I did not explicitly train Spanish to French. So, but for the earlier Model 1, the deep neural network model, this was only trained for 10 epochs. The translation got was absolute garbage. It definitely has to be trained much more. And papers talked about switching optimizer if nothing was changing during a certain number of epochs. That might also be very helpful. Future directions, it would have actually made this actually really good. Definitely deeper stacked layers. I feel like for the coder decoder, they definitely will be very useful long term. They talked about a Banadal attention layer, but essentially this doesn't actually know, like it doesn't have any real context. So if we had this layer, it'd be super useful. In addition to that, beam search to actually be more useful in the full sentence. Switching to SGD when the loss becomes stuck, because Adam's not great at certain cases. The word map could definitely, we could increase the number, especially when we get more sentence pairs essentially, and we increase the number of epochs. In addition, a lot of these functions, such as the bind to attention layer, the beam switch, are actually in TensorFlow 2, so that's definitely a different direction that could be taken. And these are some references if you guys are interested in just learning more about the papers and just how this actually all works. Thank you.